Welcome to ECOFusion, a cellular, electron-cooled approach to fusion energy production. This webinar consists of 4 videos. Video 1, which you are watching now, will begin with an introduction to the energy problem. It will then go into some overall goals of a fusion energy production system, and wrap up with an introduction of the ECOFusion concept, which will include a review of the physics of electron cooling. Videos 2 and 3 are meant for a scientific audience. In them we will set some initial parameters of the ECOFusion device, and then go into detail on the ion and electron beam physics and optics. Finally, we'll look at some component designs for the ECOFusion system. The last video, Video 4, will conclude the webinar by looking at some summary predictions on device operation. The world energy situation today is a topic of great concern. Presently, the world gets much of its energy from fossil fuels. Fossil fuels have 2 problems. They produce CO2, and the supply is limited. The problem with CO2 emissions is that they are changing the chemical composition of Earth's atmosphere, with unknown consequences for our future climate. Also, the limited fossil fuel supply within the Earth is making it harder and harder to meet the world's energy needs. The era of cheap oil may well come to an end in the next few decades. As we look for alternatives, one of the first possibilities is traditional nuclear fission energy. But fission energy has had a problematic past, with accidents, the problem of nuclear waste, and the possibility of weapons proliferation all being undesirable side effects. Solar, wind, hydro, and renewables also receive great interest presently. But when one looks at the resources needed to generate power from these approaches, one quickly realizes that meeting the world's energy needs with renewables will not be eco-friendly at all, due to the large amount of land and material needed to produce the amount of energy we presently use. The one known process that holds the greatest promise for solving the world's energy needs is fusion, which holds out the promise of clean, essentially limitless power. Unfortunately, fusion energy has been very hard to master, as scientists have predicted that we are only 20 years away, but have been saying that for the last 50 years. Next, we'll look at some overall goals of a fusion energy production system. So what is the goal? We wish to produce clean, essentially limitless power using the reactions of taking deuterium and tritium and producing helium-4, a neutron, and 17.6 MeV, and then take the neutron generated in that reaction and impinge it upon a lithium-6 blanket around the device to make tritium, helium-4, and 4.8 MeV of additional energy. Note that the neutron in the first reaction is used to produce tritium, and that the tritium in the second reaction can be used again in the first reaction. This seems simple enough. Just bring enough deuterium and tritium into collision at the right energy and one could fuel the world. However, 3 problems exist. There's a space charge repulsion of the positively charged deuterium and tritium ions that make it difficult to get them close together. Secondly, the ions must be accelerated or heated to the appropriate energy for the reaction to occur. And lastly, most particles will not fuse even if they are at the right energy. In addition, we must have a device that achieves a power out divided by power in ratio of at least 2 to 3 in order to overcome the Carnot cycle that's involved in transferring the heat energy into a useful electrical energy. To maximize the ratio of power out over power in, 3 attributes are needed. First, we must maximize the power out by overcoming the space charge repulsion. To do this, we can introduce electrons to neutralize that space charge. Secondly, we need to maximize the power out by getting the particles to the appropriate energy for the reaction to occur. We should try to get the center of mass energy as close to the peak of the cross-section as possible. Thirdly, we want to minimize the power in by recycling the particles. This way we can give the particles many chances at fusing and supply the input power only once. This slide shows plots of the cross-sections of reactions useful for fusion energy generation as a function of the center of mass energy of the particles involved. A cross-section is essentially a measure of how likely it is that the reaction will occur. As can be seen, the deuterium-tritium reaction is the most promising fusion reaction, and it is the one used in the present ECOFusion design. Other reactions of interest include the deuterium-helium-3 reaction, as well as the deuterium-deuterium reaction. The reason for the interest in the deuterium-helium-3 reaction is that the end products of the reaction are both charged, and that leads to very low shielding requirements for the deuterium-helium-3 reaction. The reason of interest for the deuterium-deuterium interaction is because its end products include a helium-3 ion and a tritium ion, and therefore one could use the deuterium-deuterium reaction to provide the fuel for the deuterium-helium-3 and deuterium-tritium reactions. So why don't we do fusion the easy way? The easiest approach would be to make a polymer film with a high tritium content and impinge a deuterium beam on that film. One could then recover the energy of the spent beam or use electron cooling to recycle the spent beam back to the film. The problem here is that much more power is lost to DEDX than is gained by fusion. DEDX is the process wherein ions lose their energy to electrons present in the matter. These DEDX losses rule out controlled beam solid, beam liquid, and beam gas approaches. As an aside, inertial confinement and H-bombs work by having the fusion happen so fast that the particle densities remain high for a short period of time and a burn is achieved during that short period of time. But what about a beam plasma approach? The problem here is that the beam must get into and out of the plasma, and the confining apparatus of the plasma must be passed. Either the holes penetrating the apparatus must be large, which has problems with regard to the plasma confinement, or single scattering losses will be large in the beam, and the beam particles will be intercepting the apparatus. But what about a pure plasma approach? Well, the tokamak has held out promise for decades, but to date, particles escaping the magnetic bottle have proved too problematic to achieve commercial fusion using a tokamak. Hence, the one remaining possibility is to explore beam-beam fusion. Now we'll move on to an introduction of the ECOFusion concept and do a review of the electron cooling process. This slide shows two figures of relevance for the ECOFusion system. In the top figure, we see a view of the interaction region of a single ECOFusion cell. As can be seen, the tritium ions move in the opposite direction as the deuterium ions in their overlapping straight section. The green rectangles in the figure indicate solenoid magnets that focus the beams tightly to small spot sizes where they interact. It's the presence of those small spot sizes that increase the density of the beams, which in turn increases the amount of output power of the ECOFusion device. Also important to the system are the presence of electron beam systems. Electrons are formed in guns and are bent and then merged to overlap the ion beams. The ions then lose their velocity errors to those electron beams, and once the electrons have completed their function, they are bent out of the system and collected efficiently in electron beam collectors. The bottom diagram shows a three-ring ECOFusion configuration. In the ring on the left, the deuterium ions circulate the system in a counterclockwise fashion. The deuterium ions start at the deuterium ion source and are then injected at a small angle into the electron beam. The electron beam then straightens out the trajectories so that they can circle around the system and return back to their injection point. Once the ions reach the injection point, additional ions are forced back upon them, and this then increases the current in the system. By continually inserting particles over and over again, the currents are gradually brought up to the high level that's needed for ECOFusion operation. The middle ring does the same technique with tritium ions, and the far right ring does the same thing again with deuterium ions. By arranging the systems to have different ion species in every other ring, the correct deuterium-tritium reactions are found at each overlapping region. We'll now add some animation to the system. Here we can see the tritium and deuterium ions entering the system, and we can see how they undergo collisions in their mutual overlapping straight sections. Next, we should discuss how the various competing fusion systems meet the three requirements identified earlier for a functioning fusion power source. Our first requirement was to maximize the power output by overcoming the space charge repulsion of the colliding particles. In a tokamak, trapped plasma electrons provide the needed neutralization. In the ECOFusion device, the electrons are trapped by the space charge of the beams in the non-cooling regions, and there's a beam-beam overlap between the electron beam and the ion beam in the cooling regions. In each case, electrons are present to neutralize the ion space charge. Secondly, we needed to maximize the power output by getting the particles to the appropriate energy for the reaction to occur. The tokamak relies on heating the plasma, resulting in a thermal distribution of particle velocities. This may get as much as 10% of the particles to the right energy. In the ECOFusion device, we rely on direct acceleration of the particles, which gets 100% of the particles to the desired energy for fusion. The third need was to minimize the power in by recycling the particles. The tokamak achieves this by using magnetic confinement. Both the ions and the electrons are trapped by magnetic fields to keep them in the system, allowing multiple passes of the ions against each other in an attempt to fuse. For ECOFusion, the confinement is that which is standard for particle beams, using dipoles, edge angle focusing, quadrupoles, and solenoids to do the focusing of the beams to keep them in the system. In addition, ECOFusion uses electron cooling to correct stray particle trajectories to give them another chance at fusing as well. So what is electron cooling? Electron cooling had its origins in work done by Spitzer in 1956, who showed that warm ions come to equilibrium with cooler electrons in a plasma. As an ion traverses through a plasma, it will attract the electrons due to the opposite charge between the ion and the electrons. The energy imparted into the electrons will slow the ion down until the ion comes to thermal equilibrium with the electrons. In 1966, Butker realized that an electron beam is simply a moving electron plasma. One could therefore superimpose an electron beam on the ion beam to cool it. The electrons would leave an electron gun and be steered almost into the ion beam by solenoids. Then, a toroidal bend would overlap the electron and ion beams. The ion and electron beam will then travel together, and with the ions losing their velocity errors to that electron beam. A downstream toroid would then gently take the beam out of the ion beam, and solenoids would then direct the electron beam into an electron collector where they are efficiently collected. Here we see ions entering the system with some random velocities, and then the ions are superimposed on an electron beam, which corrects those trajectories to leave an ideal ion beam at the end of the process. Electron cooling has now been used around the world in many, many laboratories, and the process is very well understood with some equations for the cooling time depicted here.